When coding in a programming language, we use a bunch of features and functions that are for us for free. They just work. But I'm curious about how they work internally. And in this video, I'm starting a series about how Swift works under the hood, which is the foundation of this YouTube channel. We're gonna start with one of the most common methods in Swift Foundation, random. With random, we can generate random values from a bunch of types, for example, integers, floats, doubles, and booleans as well. My name is Pete, and in this video, I will show you two use cases, how to generate booleans and integers. Let's get started. For this explanation, I've downloaded Swift source code to my computer. I'll start by opening bool.swift, which contains both the bool initializer and more methods, including the random function we are looking for. Right off the bat, we can see just two lines, a variable g that holds a SystemRandomNumberGenerator and a return statement returning another random function, but providing this number generator has in-out parameter. SystemGenerator is the default source of random data in Swift. Every random function calls this generator to get random numbers when they need it. We're going to talk more about it in just a bit. For now, let's explore this other random function with parameter. This function expects a generator that conforms RandomNumberGenerator protocol, which is what SystemRandomGenerator supports. Now, given this object, we call the function next to generate a new random number of type uint64. Why that type exactly? Because we need a 60-bit number, large enough to make this shifting operation 70 times to the right. If you don't know what is shifting, don't worry, I can explain it. However, I want to play a game with two dices. If I got 7 or more, I will explain you. If not, that will be your homework. Investigate what is that. You ready? Oh, I'm sorry. We got less than 7. It's your deal. Just kidding. Let me explain you. Let's say we have this 8-bit number, 211. In binary, that looks like this. Sometimes we need to move the bits of a number left or right to modify its value. This is where bit shifting comes in. In Swift, we have two operators for this, right shift and left shift. Each of these operators expects two parameters, the number to shift and the number of positions to shift. For example, if we use right shift to move the bits of 211 two positions to the right, this will move the third and fourth bits to the first and second positions, creating a new number, in this case 52. In contrast, if we use left shift to move the bits two positions to the left, now we are pushing bits in the opposite way. In this example, the number is an uint8 type, meaning that whatever bit pushed out of this 8-bit limit will be ignored, transforming the original number into 76. However, if this was a 16-bit or higher, the result would have kept all its bits and transforming the number into 844. Now that you got the idea, why is this useful? To keep it simple, it's an incredible fast and efficient way to perform certain operations at low level. For example, performing extremely fast multiplication and divisions, working with encryption algorithms, image processing, and why not, generating random numbers. There's a lot to explore in bit manipulation, but that will deserve a dedicated video. So let me know in the comments if you would like to learn more about it. And don't forget your like and subscription. All this content is for you and for free. Alright, let's go back to the random function. Okay, recap. We generate a 64-bit random number using our generator. Then we applied a right shift of 17 bits, essentially discarding the less significant 17 bits and keeping the remaining higher bits. Next, we apply a bitwise AND operation with 1. This operation isolates the less significant bit of the shift number, meaning we only care about whether that bit is 0 or 1. If the bit is 1, the AND operation produces 1, making the comparison with 0 false, so the function returns false. If the bit is 0, the AND operation produces 0, making the comparison true, so the function returns true. And that's how Swift generates random Bool values, by extracting a single bit from a randomly generated number. Now, many of you may be wondering why shift 17 bits to the right? How was that number determined? And that's a great question. And to be honest, I don't have a definitive answer, but here is my theory. If we look at past commits in Swift source code, we can see that a few years ago, this function used a modulo operation instead. It simply checked whether a random number was even or odd. That approach is definitely easier to understand, but I believe the reason for this change has to do with the theory behind generating fair random numbers, ensuring that all possible outcomes have an equal chance of occurring. We'll explore more about this fairness consideration when we get to integers. But back to the question, why 17? Honestly, it seems a bit arbitrary. Maybe there's some deeper mathematics reasoning behind, or maybe this was an empirical chosen number to improve distribution. I don't know for sure, but what matters is that this kind of refinements are part of making random numbers generation more robust and reliable over time. Now that we understand how Swift generates random Boolean values, let's take a look to the actual random number generator behind it, SystemRandomNumberGenerator. Let's click on it and jump to the definition. Here, we'll find the implementation of the next function. First, it declares a uint64 variable named random, which will store the generated number. Then, it calls a low-level Swift standard library function, Swift stdlib random. But what exactly is happening here? When you see an unsafe pointer wrapper in Swift, it usually indicates interoperability with C or C++ APIs. That's exactly the case here. If we dig deeper, we'll find that this function is actually implemented in random.cpp, where it ultimately calls arg4randomBuff, a well-known C function that generates cryptographically secure random numbers. arg4randomBuff is a C function designated to fill a memory buffer with random bytes. Here's what happens in this case. The random variable acts as a buffer where the generated value will be stored. The second argument specifies the number of bytes to generate. Since uint64 is 8 bytes, arg4randomBuff will fill 8 bytes of random data. Once this function completes, the random variable holds a random 64-bit number, which is then returned. And that's the magic behind SystemRandomNumberGenerator in Swift. It simply calls the secure random number generator from the operating system and provides a 64-bit random value. Once we have a 64-bit random number, each data type, whether bool, int, or another, can manipulate it as needed to produce a useful result to the user. I would say you should use this default random number generator 99% of the time, unless you have a very specific reason not to. For example, your app requires a custom random generator algorithm, or you want to learn how things work under the hood, just like I'm doing in this video. Either way, yes, we can build our own custom random number generator. Let's see how, right now. For this demo, let's create a command line project and define a struct that conforms to the random number generator protocol. Don't forget to import foundation. The only requirement for this protocol is to implement the next function, which we saw earlier. Alright, what now? The next function needs to implement the algorithm to generate random numbers. From here, you can implement whatever algorithm you have in mind. But to keep things simple, today we'll use one of the most common methods, the linear congruential generator. The formula for this approach looks like this, where xn is the last generated random number. The initial x0 is the seed, which we provide when we initialize the generator. A is a multiplier. Choosing a good value ensures a well-distributed sequence of random numbers. C is the increment, helping avoid repeating cycles. And M is the modulus, defining the maximum range of values. There's a lot of theory behind this, but I will leave a link in the description if you want to learn more. Now, let's implement this in code.
starting with setting up a seed, the foundation of the random sequence. Next, let's define the constants for the formula. In this example, we'll use a multiplier 5, increment 3, and modulus 16. Everything looks good. Now let's use our custom generator to generate random Boolean values. We'll initialize the generator with a seed of 7 and generate 5 random Booleans. Now let's run this and see the results. Wait, something seems off. All values are true. Let's try generating 20 values instead. It's always true. The generator works fine, but the random booleans are always true. Can you figure out why? Pause the video and think about it for a few minutes.
One eternity later.
Okay, let's see the problem. Let's go back to the random function in the bool type. As we saw earlier, we are shifting bits 70 times, which means the random number must be large enough to still have meaningful bits left after shifting. Currently, all our generated numbers are too small. They're effectively becoming zero after shifting. That's why our comparison is always true. To fix this, let's use larger constant for our generator. Okay, question. Why these numbers? These constants are well-known values for linear congruential generators and are documented in Wikipedia. You don't need to fully understand them right now, but the takeaway here is that larger numbers improve randomness and prevent bias. Okay, let's run one more time. And boom! What's going on here? The crash happens because the numbers are too large to fit in a uint64 without overflowing. We can fix that using overflow operators. Let's add an ampersand in the multiplier and addition operators. If you want to learn more about overflow operators, check out my other video, link in the description and at the top of the screen. Okay, let's run it again. Great! Now we have a good distribution between true and false values. This is way better than our previous implementation.
Great! Now we know how to generate a random Boolean and also a custom random generator. Now let's finally review the way to generate random integers.
The random function for integers is quite similar to the one for booleans. Both use the default SystemRandomNumberGenerator and call a function that accepts a generator as input. However, the key difference is that for integers, we can generate a random number only within a provided range. As you can see, I added some print statements with fun messages. That's because I had to debug the Swift source code and recompile my own version of Swift to fully understand how this random function works under the hood. By the way, if you're curious about how to compile your own version of Swift, check out my video in the description. Okay, let's jump into the internal random function. There are several versions, but for this case, let's explore the one that uses a range of type closed range. The first line calculates the distance between the lower and upper bounds using magnitude, which ensures the value is always positive. Why magnitude? Because it converts values to their absolute representation, which is helpful for negative ranges. Delta represents how many possible numbers exist between the upper and lower bounds. For instance, in this example, even though the range is reversed, the delta is 9, from 1 to 10. For 99 of cases, we add 1 to delta to include the upper bounds and cover the entire range. However, there is a critical edge case. In this case, adding 1 will cause an overflow, making delta wrap around to 0. That's why we return a random value directly from the generator without adjusting the range. Now, let's break down the return statement. Here's what's happening. We are converting the lower bound to a positive magnitude. Next, we are adding a random number from 0 up to delta. And lastly, we convert the result back to the correct type using truncating if needed to handle overflow. In simple terms, we are picking a random offset from the lower bound within the range. In the example from 1 to 10, we are setting 1 as the lower bound, and then we calculate how much we need to add based on the generated random value. What is interesting here is that we can basically get any 64-bit number. How can we filter a value to get something that fits in the range? Let's explore next function with upper bound now. If we read the first comment in the definition of this method, it states that this function returns a random value less than the provided upper bound. The goal of this function is to generate a random number between 0 and upper -1. It's a low-level function that helps random work properly when a range is provided. In our example, the original delta was 9 from 10 minus 1, and we added 1 to cover the entire range, making the delta 10. This delta becomes the upper bound passed to this function. So next upper bound will return a number between 0 and 9. And as you saw, the lower bound is set to 1 already, meaning that we can correctly generate a number within the range 1 to 10. Now, how can we get that number? The function starts by generating a random number using the same next function we discussed earlier. Now, here's where the magic happens. Let me explain this line of code with a simpler example. Imagine you have these two numbers. x1 is an 8-bit number with a value of 200, and x2 is another 8-bit number with a value of 50. If we try to multiply these two numbers, we will get an overflow crash because the result will be 10,000, which is far larger than the maximum value 255 that can fit into an 8-bit number. Of course, we could apply an overflow operator to handle this. However, this will only prevent the crash by wrapping the number to fit within the 8-bit limit. It will discard any extra bits that overflow the range, losing the actual result. But what if we want to store the entire result, including the overflow part? That's where multipliedFullWidth comes to play. The multipliedFullWidth method preserves the full multiplication result in two parts: low, which is the part that fits within the 8-bit limit, and high, holding the overflow bits that didn't fit. Let's visualize this in binary. The low part stores 16, the value that fits into 8 bits, and the high part stores 39, which is the overflow portion. Together, they represent the full value of 10,000. This is extremely useful for operations with large numbers that can fit into a single data type. Now, let's apply this concept to the random number generator. Imagine the random number. It's the largest possible 64-bit number, which is this number here, or just a bunch of 64 ones in binary. Now, what will be the result of multiplying this number by the upper bound equal to 10? Now 500. Now a billion. And lastly, 25. I think you're start getting the idea. The high property will give you always the max possible value, meaning the upper bound minus 1. In other words, based on the generated random number, we apply multipliedFullWidth to force an overflow. The result stored in the high property is the value that will always fit within the specific range. Clever, huh? Let's go back to the random code. If we scroll down, yes, we return high, and we add this number to the lower bound we saw earlier. That is how the int random numbers are generated. Lastly, what about this code? This part handles a subtle problem called Modulo Bias, which I'll explain with an analogy that even my grandma will understand. Imagine we are giving away raffle tickets to 10 people from 0 to 9, but we only have a big roll of 256 tickets, numbered 0 to 255. To make it fair, we decide that we'll take each ticket number divided by 10 and use the remainder as the person's number. That means ticket 7 goes to person 7, since 7 modulo 10 is equal to 7. Ticket 42 goes to person 2, ticket 250 goes to person 0, and so on. Everything seems fine, right? Now, let's count how many tickets each person gets. From 0 to 249, everything is perfect. Each person gets exactly 25 tickets. That is because 250 divided by 10 is 25. But from 250 to 255, there are only 6 tickets left. Not enough for everyone. Those last tickets go only to person 0, 1, 2, 3, 4, and 5. People 6, 7, 8, and 9 are not getting an extra ticket. This means some people get more chances to win the raffle than others. This is called Modulo Bias, because some outcomes are more likely than others. To keep things fair, we have to throw away the extra unfair tickets from 250 to 255 and pick any new random number instead. That's what this Swift code does. It checks if the random number is in the unfair range, meaning this condition is true. If it is, we throw it away and generate a new random number until we get a fair distribution. This process is called rejection sampling. Suppose Swift generates this number, and our range is 10. Here, low property is 4, which is less than upper bound. So Swift rejects this number and tries again until it gets one outside the unfair range. Technically, this could cause an infinite loop, but don't worry, it's extremely unlikely because the chance of landing in the unfair range decreases rapidly, and the algorithm is based on Lemaitre's nearly divisionless method, a well-known approach for efficient unbiased random number generation. If you want to learn more, check out the paper by Daniel Lemaitre in the description below. And that's how Swift keeps random number fair and efficient under the hood.
That was awesome. We learned together how to generate random numbers and how there are a lot of mathematics and distribution under the hood, which is great. I don't know you, but I learned a lot making this video. And if that's the case for you, don't forget your like and subscription because that helped me that you like this content and you want more. And if so, then I will prepare more videos like this in the future. This video took many months of preparation and investigation, so I really appreciate your patience as well. Alright, that's all I got. My name is Pete, and this is If and Tips. Thanks for watching, and have a great day.